It's the 1st of December, 1990, more than 100 feet beneath the seabed of the English Channel, and two workers are closing the last narrow gap of chalk between two tunnels that have spent years boring toward each other from opposite coasts. One, an Englishman named Graham Fagg, has come from the cliffs of Dover. The other, a Frenchman named Philippe Cosette, has come from Calais. Neither tunnel could see the other coming. Only careful, continuous surveying kept both machines on course. When Fagg and Cosette finally break through and shake hands, it marks the first time in roughly 8,000 years that a person could cross from mainland Europe to Britain without getting their feet wet. Stick around, because getting to that handshake meant solving nearly 2 centuries of failed attempts and building one of the most technically demanding tunnels ever attempted by human beings. The idea of tunneling under the English Channel is far older than the technology needed to actually do it. In 1802, a French mining engineer named Albert Mathieu Favier proposed a tunnel lit by oil lamps, complete with horse-drawn coaches and an artificial island in the middle of the channel where the horses could be swapped out. Nothing came of it. Decades of surveys and proposals followed, and around 1880 and 1881, British railway entrepreneur Edward Watkin and French contractor Alexandre Lavallee actually started digging, using an early tunnel boring machine on the British side and a similar one from Sangatte on the French side. Real progress followed on a real tunnel. Then it stopped. The British military raised fears that a tunnel could become an invasion route for a hostile European power, and in 1883 the project was abandoned outright. That fear didn't go away quietly. During the Paris Peace Conference in 1919, British Prime Minister David Lloyd George pushed the idea again, hoping to reassure France of Britain's commitment to defend it. France itself was broadly receptive, and the real resistance remained on the British side, especially among military leaders. In the 1920s, Winston Churchill became an outspoken advocate, arguing in print that the invasion fears were overblown and that a tunnel could actually be defended more easily than an open coastline. It didn't matter. When the Second World War arrived, the fear resurfaced in an even stranger form. One British wartime naval assessment speculated that Hitler could use slave labor to dig 2 channel tunnels in as little as 18 months, and rumors spread that Germany had already begun. By the 1950s, the rise of air power had made the invasion argument mostly irrelevant, and both governments quietly returned to serious technical surveys. The two countries actually agreed to build a tunnel in 1964. After almost 2 centuries of talking, Britain and France finally started digging, breaking ground on both sides of the channel in 1974. Then, almost immediately, they stopped again. In January of 1975, Britain's government cancelled the project, spooked by ballooning cost estimates and a shaky economy. The tunnel boring machine that had been readied on the British side sat unused for years afterward. The idea finally found the political momentum it needed in the 1980s. In 1981, British Prime Minister Margaret Thatcher and French President François Mitterrand agreed to set up a working group to study a privately funded crossing, and by 1985, 4 very different proposals had made the shortlist. One was a 35-kilometer suspension bridge built from an exotic fiber called paraffin, carrying road traffic inside enclosed concrete tubes slung nearly 100 meters above the water. Another proposed a tunnel running between artificial islands built mid-channel. A third called for a set of giant road tunnels with ventilation towers rising straight out of the sea. In January of 1986, the governments chose none of them, instead selecting a comparatively conservative twin-bore rail tunnel, largely because it caused the least disruption to shipping, posed the smallest environmental risk, and was the most likely to actually attract private investors. The following month, Britain and France signed the Treaty of Canterbury, setting out the legal jurisdiction of each country over its half of the future tunnel, deep under the seabed. Getting the project through each country's own government was its own fight. France's National Assembly approved it. In Britain, the opposition was louder. The cross-channel ferry industry campaigned hard against a fixed link that threatened its entire business model, and despite that sustained opposition, the bill passed the House of Commons by a vote of 94 to 22. What made this project genuinely unusual, though, wasn't just the engineering, it was the money. Unlike almost every other infrastructure project of its size, the fixed link itself was financed without government grants or government guarantees. The consortium raised money through bank loans, a massive letter of credit, and, remarkably, a public share offering advertised on television and in newspapers, letting ordinary investors buy a literal piece of the tunnel. At 1985 prices, the whole project was projected to cost £2.6 billion. By the time it was actually finished, the real cost had climbed to £4.65 billion at those same prices, an overrun of roughly 80%. Digging the thing in the first place meant solving a geological puzzle first. Beneath the seabed lies a layered mix of chalk formations, and engineers needed a layer soft enough to bore through quickly, but solid enough not to collapse or flood under enormous water pressure. They found their answer in a band of rock called chalk marl, roughly 90 feet thick, impermeable enough to keep water out, and just soft enough to cut without heavy reinforcement. It made up about 85% of the entire route. The layer behaved differently on each coast, though. On the English side, it sat nearly flat and stayed relatively dry, so crews could use simpler, faster machines with an open cutting face. On the French side, the same layer tilted far more steeply and let in much more water, forcing engineers toward heavier machines that could seal themselves shut and balance the pressure of the surrounding earth against their own cutting face to keep the tunnel from flooding as they advanced. 11 tunnel boring machines in total, 5 French and 6 British, chewed through the rock from both coasts at once. On the wetter French side, the ground-up chalk was mixed with water and pumped out as a slurry. On the drier British side, the excavated chalk was hauled out and much of it reused to build new land, while crews behind the machines assembled rings of concrete or cast iron to line the tunnel as they went. The French machines were named after women: Brigitte, Europa, Catherine, Virginie, and Pascaline. The English machines got dry technical names instead. At least one of the British machines finished its work by driving itself steeply downward and burying itself in the rock rather than being hauled all the way back out, since retrieving it wasn't worth the cost. Boring the hole turned out to be only part of the challenge. A train moving at speed through a long, narrow tunnel behaves almost like a piston, shoving a wall of compressed air ahead of it with nowhere to go, which drags on the train, rattles passengers, and plays havoc with ventilation. Engineers solved it with nearly 200 pressure relief ducts connecting the two rail tunnels, giving that compressed air somewhere to escape instead of fighting the train the whole way across. Heat posed a similar problem. Calculations showed that friction and braking from high-speed trains would push the tunnel's temperature above 120 degrees Fahrenheit if left unmanaged. So engineers built what was then Europe's largest cooling system, hundreds of miles of pipes circulating chilled water to keep conditions survivable. The three bores also needed a way to stay safe and operational even when something went wrong. Every 375 meters, a cross passage connects the two rail tunnels to the service tunnel running between them, giving passengers and crews an escape route if a train ever had to be evacuated. Deep under the seabed, two enormous crossover caverns, among the largest artificial underwater caverns ever built, let trains switch from one rail tunnel to the other behind massive steel doors, so a problem in one tunnel doesn't have to shut down the whole crossing. Not all the excavated rock stayed underground either. Millions of cubic meters of chalk spoil came out of the English side alone, and rather than dumping it at sea, engineers piled much of it behind a new seawall at the base of the cliffs, reclaiming dozens of acres of land that didn't exist before construction began. That reclaimed ground is now a country park and nature reserve, a small stretch of England that didn't exist before the tunnel was built. None of it happened without real risk to the people doing the digging. At the peak of construction, thousands of workers were employed across the project, with daily expenditure running over £3 million. 10 workers, 8 of them British, were killed during construction between 1987 and 1993, most of them in the first difficult months of boring. All of that digging was aimed at a single, almost impossibly precise target, the exact point, deep under the middle of the channel, where the two national efforts would meet. Surveyors on both coasts had spent years establishing a shared coordinate grid using laser instruments and precision measurement across the water, then projected that grid straight down through vertical shafts to guide the machines below. No satellite positioning worked at that depth, so crews had to survey and recheck their course constantly, since even a tiny error compounded over tens of kilometers could send the two tunnels past each other entirely. When the two sides finally connected on that 1st of December in 1990, after boring roughly 23 miles from opposite coasts, the alignment was off by about 14 inches horizontally and barely more than 2 inches vertically. The tunnel was formally inaugurated in May of 1994, a year later than originally planned, with commercial services phased in gradually over the following months. French President Mitterrand and Queen Elizabeth II held a joint ceremony in Calais, their trains pulling up nose to nose after arriving from opposite directions, before both traveled back through the tunnel together for a matching celebration in Folkestone. The engineers had missed their target by centimeters. The financial forecasts missed theirs by billions. Passenger and freight demand both fell well short of what investors had been promised, and by September of 1995, the tunnel's operating company had to suspend payments on its debt just to avoid bankruptcy outright. Years of financial restructuring followed, including a major overhaul of the company's debt in the mid-2000s, before the business built around the tunnel found anything close to stable footing. The tunnel has faced other tests since. Fires aboard vehicle-carrying shuttle trains in 1996 and again in 2008 severely damaged sections of track, causing months of repairs and reduced capacity, though the tunnel's ventilation and evacuation systems meant no fatalities in either incident. The tunnel has also become a flashpoint in Europe's migration crisis since the late 1990s, and attempts by migrants to cross illegally through it have cost a number of lives over the years. In 1994, the American Society of Civil Engineers named the Channel Tunnel one of the 7 wonders of the modern world. The addition of a dedicated high-speed line into London in 2007 cut the journey between London and Paris to about 2 hours and 15 minutes. It remains the tunnel with the longest underwater section on Earth, and every single day, without much fanfare, it does something no fixed structure had done since the end of the last ice age. It lets someone walk, or at least ride, from the island of Great Britain to the European mainland without ever touching the sea. So here's a question worth sitting with. This is a tunnel that took nearly 2 centuries of false starts, cost 80% more than planned, and saw traffic and revenue fall far short of the original forecasts, leaving early investors to pay heavily for it. Given everything we know now, was the Channel Tunnel a triumph of engineering ambition worth building regardless of how badly the financial model missed the mark, or a cautionary tale about letting enthusiasm outrun the numbers? Let us know what you think in the comments. And if this dive into one of the most complicated tunnels ever bored gave you a new appreciation for what's running under the channel every time you fly over it, give this video a like, subscribe for more deep dives into the world's most ambitious engineering projects, and turn on notifications so you don't miss the next one.